Hi everyone, it's a pleasure meeting you all in my mathematics class. I am continuing with the proofs of the convergence and divergence theorems, because as I used to tell that the students must be proficient with the theorems so that they can apply to problems very confidently. So with that in my mind, I have been doing the theorems. So today, let me take this theorem. If n tends to infinity of an is not equal to 0 or does not exist, then this particular series diverges. This is the theorem. So how to prove this? So let us prove this theorem now. Let us prove this theorem. See, what does this say? That if, see, it must, limit of n must tend to a finite limit or must be equal to 0, then we can say that this series is convergent. If it is not so, it has to be divergent. So instead of now, if if this happens, then an will be a divergent series. What I am going to take is, I am going to take the contrapositive. See, what it says is that, see, if limit of n tending to infinity of an is not equal to 0 or does not exist, then this I will write here, then see, this implies, I write, this implies sigma and n is equal to 1 to infinity is n is divergent. So this is the theorem. If this is not equal to 0 or does not exist, then this is. So I am going to take the contrapositive. See, while I take the, let us take the contrapositive. What is the contrapositive? Contrapositive is if sigma 1 to infinity of an is not divergent or convergent, then limit n tending to an is equal to 0. So you see that I am taking the contrapositive. Negation of this and negation of this. Negation of this is, it is convergent. Negation of this is, it is equal to 0. So we are going to prove only this. See, what I do here is, see, let me prove this. See, proof, if you understand well how it is approached, anybody can prove this. See, what I say is, see, I will take, now let Sn be equal to a1 plus a2 dot 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 an, the nth partial sum of Sn. Then Sn is equal to a1 plus a2 dot 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 an minus 1 plus af. Now, since, see, Sn is equal to so much, so that Sn minus Sn minus 1 is equal to, you see that all this get cancelled, giving you this here. Giving you this here. Since sigma of 1 to infinity of an converges, limit of n tending to infinity of Sn, which is nothing but limit of n tending to infinity of, it is k is equal to 1 to n an is equal to SC. So I am taking like this, since 1 to infinity of an converges, let me suppose that this partial sum Sn as n tends to infinity, see this is Sn minus 1. So this partial sum Sn, it tends to S as n tends to infinity. Let us assume that this partial sum tends to S as n tends to infinity, because this Sn, sigma of 1 to infinity En is assumed to be a convergence series. Now you see that as, see, Sn tends to S as n tends to infinity, and also Sn minus 1 tends to S as n tends to infinity, as n is arbitrary. That is what we take. Okay, even if we take n minus 1, it will tend to infinity. If we take n tends to, so you see that since this sigma of 1 to infinity n converges, let us assume that, not assume, since it converges, we will take it for granted that we assume that this partial sum Sn as n tends to infinity converges to S. Since Sn converges to S, Sn minus 1 is after all, n is an arbitrary, that Sn minus 1 will also converge to S. Therefore, so you see that 1 minus 2 gives you An. See, it is An, Sn minus Sn minus 1 is equal to An. Now, let me take this. See, Sn, that is An is equal to Sn minus 1. Therefore, limit of n tending to infinity of An is equal to limit of n tending to infinity of Sn minus 1. That is equal to, see, limit of a sum is equal to sum of the limits. So this is limit of n tending to infinity of this minus limit n tending to infinity of Sn minus 1. But as I told you, Sn tends to S and Sn minus 1 also tends to S. This is equal to 0. This implies that limit of n tending to infinity of An is equal to 0. So we have got. So what is that we have proved? If An converges, then if An is convergent, then An is equal to the limit n tending to infinity of An is equal to 0. Suppose if it diverges, then it has to be. So if it is divergent, then this will not be tending to 0, or it will not be tending to a finite limit. That is the meaning of that. Okay. So this is about the first theorem. So let me pause on to the second theorem. The second theorem, that means if sigma of 1 to infinity of An converges, then a multiplication of the series by C will also be a convergent one. And you see that what it is like this. See, what I do here is, see, given sigma of 1 to infinity of An converges. Let Sn be the partial sum given by A1 plus A2 up to An. And because of 1, limit of n tending to infinity of Sn is equal to limit of n tending to infinity of 1 to n a k. Now this will be as n tends to infinity. Let us suppose that it tends to S, finite limit C S. Yes. Now C into Sn. C into A, I will write it. See, now C sigma of 1 to infinity of C of An is equal to C into, see, this is C into C into limit of n tending to infinity of limit of n, it is like this, limit of n tending to infinity of C of S1 plus, A1 plus A2 dot AN. That is limit n tending to infinity of C of A1 plus C of A2 plus C of A3 plus C of A4. That is limit n tending to infinity of k is equal to 1 to n. It is C of AK, that is equal to, C can be taken outside always. So you see that C into, it is C into limit of n tending to infinity of 1 to infinity of 1 to n of AK. But we have taken this 1 to n of AK infinity, say by 2. So this is equal to CS by 2. Therefore, sigma of 1 to infinity of C of An is equal to, it is C, but S is equal to C. What says S? So this is equal to C into 1 to infinity of C of An as 1 to infinity of An is equal to S. So this is how we prove this. See, what we do here is, it is given to be convergent. So let me take the partial sum Sn is equal to An. Therefore, because this is convergent, limit n tending to infinity of Sn is nothing but n tending to infinity of 1 to n of Ak is equal to S. Now you take multiply this by C. So integral, that is sigma of C of An is equal to, it is nothing but C of A1 limit n tending to infinity of C of A1 plus C of A2 plus C of A3 like this. And this is nothing but limit of n tending to infinity of 1 to n of C of Ak, where k takes the value 1 to n. And this is nothing but, since C is a constant inside, that can be removed, can be taken outside, that limit of n tending to infinity, that is sigma of 1 to infinity 1 to k 1 to n Ak is equal to, see, this value of this we have assumed to be what? Our S. So this is equal to S. But S is nothing but what? Your S is nothing but your 1 to infinity of An, because this is, we assume that this is convergent, and let us suppose that this is convergent to S. Therefore this is sigma of 1 to infinity of An is equal to S. Therefore this is equal to CS, and in the place of CS, let me put this 1 to infinity of An. Therefore sigma of 1 to infinity of C of An is equal to C into 1 to infinity of An. So this is how we prove this theorem. Now let me pause on to next one. So here you see that if An and Bn are convergent, then sigma of An plus Bn converges to the convergent limit of the first series plus the convergent limit of the second series. If one of them diverges, then the an plus bn series diverges, and if both of them diverge, naturally becomes a divergent series. Now you see that how to do this. So let us suppose that, see, let Sn is equal to a1 plus a2 dot 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 an, the partial sum, then limit of let an and limit of n tending to infinity of Sn p is equal to Sc, and Tn, see, Tn be equal to b1 plus b2 plus dot 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 plus bn, and limit of n tending to infinity of Tn b is equal to Tc. Now an plus bn, see, now a1 plus a2, a1 plus b1 plus a2 plus b2 plus dot dot dot, which is nothing but plus an plus bn, and this now is a1 plus a2 plus a3 dot 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 up to an plus b1 plus b2 plus dot 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 up to bn. Now that is, therefore I will write it here. Now sigma of 1 to n of ak plus bk is our a1 plus b1 plus dot 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 up to an plus bn. That is equal to, see, that is equal to, it is a1 plus a2 dot 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 en plus b1 plus b2 dot 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 up to bn. So this is nothing but I varying from 1 to n of ai plus j varying from 1 to n of bj. But we must know that this is nothing but our partial sum. This is nothing but our partial sum Sn, and this is nothing but our partial sum Tn. Now if we take the limits, therefore limit of n tending to infinity of sigma of 1 to n ak plus bk is equal to limit n tending to infinity of Sn plus Tn. That is equal to limit n tending to infinity of Sn plus limit n tending to infinity of Tn, partial sum. Therefore, so this we have taken, so we will call it as 1. So this is equal to S plus T by 1. S plus T. But this is nothing but sigma of 1 to infinity of An plus 1 to infinity of Bn. So you see that sigma of limit n tending to infinity of ak plus bk is equal to the tends to the limit of, see, this is a convergent series, it tends to yes, and this is also a convergent series, it tends to t as n tends to infinity. Therefore, you see that the sum of if ak and bk are convergent, then the series obtained by the sum, adding the sum of the two series will be equal to s plus t, where s is nothing but the convergent value of the sequence sigma of 1, say sigma of 1 to infinity of an, and the convergence limit of n is equal to 1 to infinity of bn, which is equal to t. Therefore, you see that now, so if Sn sigma of 1 to infinity of, that is sigma of 1 to infinity of an and sigma of 1 to infinity of bn are convergent, then an plus bn, this convergent 1 to infinity, will be converging to the limits of the individual sequence, the limits of the individual sequence. Now, if say by chance you see that if let sigma of 1 to infinity of a and b divergent, then what will happen to the series now? So this will be nothing but, therefore we get, see, let us call this as our 2. Say let us call this as our 2. See here you see that, say I will take this, I will not call it as 2. Therefore we get this sequence, namely sigma of, therefore we get sigma of 1 to infinity of an plus bn will be equal to sigma of 1 to infinity of bn plus sigma of 1 to infinity of bn, sigma of 1 to infinity of an plus sigma of 1 to infinity of bn. But this is nothing but, this is a divergent series. That means this is divergent, sigma of 1 to infinity an plus, I will take it as t, because this is converging to t. Therefore, you see that this is a divergent series, this is a divergent series, but whereas this is a convergent one. So this implies that since sigma of 1 to infinity of an is divergent, 2 is divergent. And if both sigma of 1 to infinity of an and sigma of 1 to infinity of bn are divergent, then 1 to infinity of an plus bn is also divergent. So this is what we get. So this is a very simple, and we can very easily do this. So you see that in the first case I have taken this ak, a1 plus b1 we have written here, and you see that this is nothing but a1 plus a2 plus this thing an, and this is the partial sum, and I write it in this way, and I take n tending to infinity. So here one, now this one, therefore n tending to infinity will be equal to, you allow this n to tend to infinity, because, and we assume that because Sn, this sequence and this series both are convergent, this Sn tends to S and this Tn tends to T, therefore the whole series is convergent. Even if one of them is divergent, the whole series is, the ak plus bk, k running from 1 to infinity, will be a divergent series. And likewise you see that even if both are divergent, the whole series will be divergent. And so this is about the convergent and divergent sequence. I have done 3 theorems here. We will see more theorems in the coming days, so that you will get conversant with the theorems, and also I will help you how to apply the theorems to your problems. Okay, thank you, and do not fail to subscribe to my channel.